Good morning, class. We will be looking at solid slab spanning in two directions today. We have already treated one-way slab, and now we're looking at it in two directions. That is, when a slab is supported on all four of its sides, it's effectively span in both directions. So we are looking at the the design of this particular kind of slab, and the amount of bending in each direction depends on the ratio of the two spans and the condition of restraint. Now, then let's say if the slab is square and the restraints are similar about the four sides, then the load will span equally in both directions. That's it. For instance, look at this particular one. Let's say it is square. The same load that this, let's say the same load that this particular place will be carrying, it will be in four different places. However, when we have this one is not square. This particular case is not square. The loading, the way it is at angle 45 degree here, angle 45 degree here, like this, and here where it meets it goes straight. So this side will be supported on this particular beam. This shaded portion will be supported on this particular beam. This shaded portion will be supported on this particular beam, and this shaded portion will be supported on this particular beam. Now the formula we use for two-way spanning slab is this: moment along the SS equals to this. Now I will explain how we arrive at each of this one. You already know when we say the LS is that's the short span, the LY is the long span. Or okay, it's even written here. The LY is the longer span, the LS is the shorter side, and this particular N is our load, is the total estimated load per unit area. Now the moment is equal to alpha SS NL square LS square of S, and for the moment along y axis. Now what we are having is we have moment along the x axis and moment along the y axis, and we are going to be doing calculation for each particular one, unlike where we have singly reinforced singly or one-way slab that we just use the distribution bar based on percentage. For this particular one, we will calculate it and this alpha SS and alpha SY, they are moment coefficient from this particular table. Firstly, we calculate our Ly over Ls. If it is 1.0, then our alpha SS will be this. If it is if our SS is this, and our alpha SY will be this. But however, in a situation where we have alpha SS to be 1.5, our Ly over Ls is 1.5, then our alpha SS will be 0.104. So this is how we arrive at our alpha SS and alpha SY. And once we know that, then easily we can get our moment along the S and moment along the Y axis, or moment in the Y yes, along the Y direction. So let us it says the effective depth D used in calculating ASS should be less than that for the ASY because of the different depth of the two layers of reinforcement. Now let us look at it this way. Let's say we have a reinforcement band running along the S axis and one running along the Y axis, and the one running along the Y axis is on top of the shorter one, because we believe the longer one is resting on the shorter one, and the effective depth of this particular one, because it's resting on the longer one, it will be lesser than the effective depth in this particular one will be longer than this shorter than this particular one. Let me set an example of what I'm talking about. Let's say let me try and draw let me try and see if I can draw. Okay, sorry, I think I should have an example here. Let's look at this particular one. Yes, very good. Now let's say this is our main reinforcement underneath, this is our distributed bar underneath on top. Now this is one provided based on S of S, and this one provided based on S of Y. So if you want to calculate the effective depth, which is from the top here to the centroid of this for the alpha SY, while for the alpha SS it is from this place to this particular centroid of this main reinforcement bar here. So you can see that this one is shorter than this particular one. So that's what we mean by that. So let us proceed. After calculating our alpha SS and alpha sorry, after using Ly over Ls, we got 1.4 for this particular case. Then the next thing we do is that the 1.4, we know, okay, our alpha SS is this and alpha SY is this. So using that knowledge, you can see alpha SS is this and alpha SY is this. Then we calculate our slab weight. Since we said the slab is 220 thick, then definitely we can say, okay, 220 times the unit weight of concrete, which is this, will give us this. Then we calculate our ultimate load using Eurocode 3 and Eurocode 2 rather. The 1.35 times the dead load plus 1.5 times the imposed load. You can see our imposed load is 10 here, so we got our design load there. Then we can now look at our moment along the SS and moment along the Y-axis. Moment along the SS is this formula NLS squared. So this alpha SS is what we got here, we put it here. The design load N we have, we put it here. And the LS, that's the short span. The short span, which is 4.5, we can put it here. Then we have our moment along SS, which we are now going to use to calculate our area of reinforcement the way we always do. So if this procedure, the procedure from here follows the same one for a singly reinforced. K equals to M over B D square FCU, just like this, M over B D square FCK equals to this. So from here you use the lever 0.95D and our D is this, we calculate it. Then we get our area of reinforcement, which is 588 now. Now let us, from this we provide the area of reinforcement and the number of reinforcement needed and the AS, new AS. Now the span effective depth ratio is gotten from this particular one. We have 100 AS or AS required, which is this is our AS required. Sorry, this AS required, AS provided, AS required, AS provided. So we have 100 AS required, which is 100 times this all over B times D, and our B is 1000, as I told you earlier on, and our D is 185. So when we calculate that, we have this, our row is 0.318. Now from here now we'll go and look at table at the back, which is table 6.3 and figure 6.3. We'll look at what we have there. So we using this table, we calculate our span effective depth ratio. That's the table 6.10 that I made mention of the other time. Because of time, I won't be talking about this particular table. So we calculate it 0.3 around there. Then we look at where it falls. Then if it is class 25, class 30, class 35, then we select the appropriate value. So let me go back to that one, so that so from here now from here now I think I was here. Yeah, from here now we calculate our row is 0.318. Then from this particular one we look at it from that table. Then for this one, and for that one we had 28, so we just use it use 28 to start get. Look at it, it's 24.3. Then that means our D equals to 185 is adequate, since it's less than this particular value we have here. The next thing is to calculate our moment along SY using this value and this formula. This alpha SS, don't forget, is what is the second one we got here the other time. The second one here. So we just use it and calculate our moment along Y axis. But this time around, our Z will be lesser than what we used the other time, because I said it's on top of the longer span. So we are removing one let me say 112 mm diameter bar from it. But let's say half of the, let's say we are using 12 mm diameter bar. The first 12 mm diameter bar, half of it is 6. The second half is 6. So we are using 12 mm this time around. And then we have 164 as our Z, which is what I'm going to use for our Z calculation here. Then we are providing this. This is our AS provided now, which is this. Calculate 100 AS over BD also, which is 0.24. So since 100 AS over BD is 0.24, is less than the 0.13 that is is greater, there's a greater than the 0.13, which is the minimum for transverse reinforcement. So let us look at slabs that are restrained in directions. Um, so when they are restrained, that is when the slab have fixity at the support and reinforcement is added to resist tension. Fixity at the support and reinforcement is added to resist torsion and to prevent the corners of the slab from lifting. Then the moment maximum moment per unit width are given by this formula. It looks like almost like the other one, but this time around, depending on the restraining condition. So we already know the LS and the LY. But this time around, to get this particular one, it is based on the restraining condition. Now, all these ones are for the let's say negative movement at support. This is interior panel. This for one short edge discontinuous. These are the support conditions. So I will explain this one more later as we go on with our discussion. Why this one is for the long span. This is for the short. All these ones are for the short span. No? Why this one is for the long span. So let's say we have the negative and the positive movement at mid span or at the continuous edge. So let us look at these particular instances. How many minutes in a video? Okay, I think I will use this in another video. Let me set this one first.